Let A be an m by n matrix with rank equal to m. Let B be an m tuple. Notice that the system of linear equations Ax equal to b can be written as x1 times the first column of A plus x2 times the second column of A plus all the way up to xn times the nth column of A equals b. Because the rank of A is m, that means that there are m linearly independent columns of A. And since each column of A is an element of Rm, these columns form a basis for Rm. And so we can express B as a linear combination of these m columns. And that means that in this linear combination of the columns of A, we need to set no more than m values of x to non-zero. And so the system Ax equal to b has a solution with no more than m non-zero entries. Let's look at an example. And the system Ax equal to b can be written as x1 times 1, 0 plus x2 times 1, negative 1 plus x3 times negative 1, 1 equals 2, 1. Now A has two rows, and clearly the two rows are linearly independent, so the rank of A is 2. And if we look at, say, columns 1 and 3, they are linearly independent, and so we can write 2, 1 as a linear combination of 1, 0 and negative 1, 1. And it doesn't take too long to see that we can set x1 to 3, x3 to 1, and since we don't need the second column, we'll set x2 to 0. And that gives us a solution to Ax equal to b with two non-zero entries. And this observation gives rise to the following definition. So suppose that A is an m by n matrix with rank m. Then an m element subset B of the set 1 up to n is a basis with respect to the matrix A if the columns of A indexed by the elements of B are linearly independent. In other words, these columns form a basis for Rn. So if we go back to the example, we see that B equals 1, 3 is a basis with respect to this matrix A because the first and third columns are linearly independent. Now, we can also take B equals 1, 2. This will also be a basis because the first two columns are linearly independent. The remaining choice for a two-element subset is 2, 3. But this is not a basis because the second and third column are not linearly independent. If we are given B an element of Rm, then X star is called a basic solution to Ax equals B if there exists a basis B such that Ax star equals B and X star J is 0 for all J not in the basis B. And we say that B determines the basic solution X star. So if we go back to the example here, the solution given by x1 equal to 3, x2 equal to 0, and x3 equal to 1 is a basic solution determined by the basics 1, 3. Now let's see what is the basic solution determined by the basis 1, 2. So we need to solve this system with x3 set to 0. And if x3 is set to 0, then it's clear that x2 must be negative 1 and x1 must be 3. So this basis determines the basic solution 3, negative 1, 0. Very often, once a basis B is given, this system is rewritten as A sub B times X sub B plus A sub n times X sub n equals B, where n is the set 1 up to n with all the elements in B removed. And for any subset J of 1 up to n, A sub j denotes the submatrix obtained from A by taking only the columns indexed by elements of J, and X sub J is obtained from X by taking only the entries indexed by elements of J. And with this notation, we see that the values of the variables indexed by B, which are called basic variables, is given by the inverse of A sub B times B. Variables that are not indexed by elements of B are called non-basic variables. And in a basic solution, non-basic variables must be equal to 0. In the context of linear optimization, we are interested in what are known as basic feasible solutions to the system Ax equal to B, x greater than or equal to 0. A basic feasible solution is simply a basic solution that satisfies these inequalities. The reason why we're interested in basic feasible solutions is that linear programming results are often given for problems in standard form, problems that look like this. And so basic feasible solutions are a special family of feasible solutions to this problem. It turns out that if this linear programming problem has an optimal solution, then it must have an optimal solution that is a basic feasible solution to the system. This fact is one of the key ingredients to the simplex method. The main challenges that remain are detecting when a given basic feasible solution is optimal and efficiently going through different basic feasible solutions towards one that is optimal if it exists.